our third video for chapter 12, we're going to begin with our Fick equation. And you've heard the term VO2 max several times in the course so far. I want to take some time to discuss the actual equation that's associated with VO2 max. VO2 is expressed with a V, and we've got a dot above it there. And Q, as you remember, is our cardiac output, and that's determined by stroke volume times heart rate. Well, we've got a new symbol that we haven't discussed before, A minus V O2 diff. And it stands for our arterial venous oxygen difference. So what does that even mean? Well, when we start dumping oxygenated blood off at the muscle extracts the oxygen, and then the venous blood returns the deoxygenated blood back to the heart. So if you imagine that we had 100 units of oxygenated blood and we send it to the muscle, and then the muscle gobbles up most of it and it only sends 2 units of oxygenated blood back to the heart, well, we would have an oxygen differential of 98. And that sounds like a silly example, but we're just using it to illustrate the equation. And again, the equation is our Fick equation. So when cardiac output increases during exercise, more oxygen is being transported to the working muscles. But our muscle needs a high level of capillarization for a large volume of blood to be delivered to it. Now, our aerobic training, it can increase that capillarization of the muscles that are being used for that aerobic exercise, but it will not increase the capillarization of muscles that aren't being used. So the max amount of oxygen a person can use is going to be related to their cardiac output, so the delivery, as well as how much oxygen they're able to be used by the muscle cells, and that would be the uptake. And that's what our AVO2 difference is. And let's look at our cardiac So the maximum amount of oxygen that a person can use is going to be related to their cardiac output. So that's the delivery, as well as how much oxygen is actually able to be used by the muscle cells. And that would be the uptake. That's our AVO2 difference. Next, we're going to look at table 12.4. And it shows some typical values for the components of the oxygen transport equation during maximal exercise for untrained subjects, trained subjects, and specialized endurance athletes or elite endurance athletes. The value in the final column, if we have a look there, is our cardiac output. Remember, it's symbolized by the letter Q. And our cardiac output is calculated by multiplying the values in the second column, our heart rate, by those in the third column, the stroke volume, and then converting the result from milliliters per minute into liters per minute. Now, what seems to be the difference between our untrained, trained, and elite athletes when you look closely at the chart? Our max heart rate is relatively close to one another. It's our stroke volume that's the main difference. You might also that the elite athlete has a slightly lower maximum heart rate as well. Now, when we look at our AVO2 difference at rest, our body's blood oxygen content is around 200 milliliters of oxygen per liter. And that's in arterial blood, and our venous blood is around 140 milliliters. So remember, arterial is oxygenated blood, venous is deoxygenated blood. So our AVO2 difference would be 60 milliliters of O2 per liter, and that's at rest. When we're exercising, we can see that the difference is about 2 times that in our untrained individual and almost 3 times that in our elites, athletes. Figure 12.8 is showing exercise heart rates in workload in trained versus untrained individuals. And as shown, a trained subject can work at higher workloads than an untrained subject. If you see the dotted line, here's our workload from low to high. At any workload, the trained individual is going to have a lower heart rate than the untrained individual is going to have. Now, our heart rate increases linearly with increasing workload until a maximum is reached. Trained people tend to have a bigger stroke volume, thus a lower exercise heart rate, which helps them to maintain cardiac output. So this relationship between heart rate and workload provides our basis for incremental loaded VO2 max testing. And that's a test that we do in the lab. Now we can use our sub-maximal heart rate testing and use that to predict our VO2 maximum. But remember, it's not super reliable because of the individualization of heart rate maximums, where it can be plus or minus 12 beats compared to another individual. Next, we're going to look closer at stroke volume during exercise. So our stroke volume response isn't as clear as our heart rate response to exercise that we just saw on the last slide. I said before that as intensity increases, heart rate increases as well, and it corresponds quite well to the intensity. But the stroke volume response doesn't really respond in the same way. We used to suggest that stroke volume reached maximum at approximately 40% VO2 max and does not increase further during steady state aerobic work for most people. This is referred to as the plateau response, and this was in part the reason that the lower range of preferred exercise intensity was set at 50% VO2 max or 60% of their max heart rate. And you'll still see this with the American College of Sports Medicine and with CSEP and their recommendations, where they say that with a novice exerciser, we should stay at about 60% of their max heart rate. Now, keep in mind that's with a novice exerciser. It was argued that this percentage would ensure the exerciser had reached their maximal stroke volume. Now, maybe that's true with a novice exerciser, but what about an advanced or elite trained athlete? Would they reach their maximal stroke volume at 50% VO2 max or 60% heart rate? Recent evidence suggests that stroke volume in highly trained individuals continues to increase even after 40% VO2 max. So it's important to realize that for our endurance trained athletes, that lower intensity exercise may not do enough to cause the stroke volume to really reach maximum. So it's only if the intensity is high enough that the trained individuals will reach their stroke volume maximum. Otherwise, we won't exploit the potential of our elite athlete's stroke volume. So this may explain why high intensity interval training, or HIIT training, that we'll talk about later on in the semester, has shown to be very effective as participants will reach their maximum stroke volume even in our highly trained individuals. Figure 12.9 shows 4 main types of stroke volume response with increasing exercise intensity. So we can see stroke volume here and our exercise intensity increasing here. And it shows that different subjects respond differently to increasing exercise intensity, or their stroke volume responds differently. And that's likely due to different physiological adaptations, different training backgrounds, obviously different genetics between individuals, and all of that is beyond the scope of this course and the level being a first-year course. So one result of endurance training is an increase in blood volume, and those that have a higher blood volume are going to be able to show a progressive increase in stroke volume during exercise of increasing intensity, as we see in figure 12.9. It also shows, figure 12.9, that some individuals can experience a drop in stroke volume as the exercise intensity increases. And we see that here with our dotted line. This explains why, for some individuals, we can see good improvements in VO2 max with just moderate intensity exercise. The reason for this drop in stroke volume as our exercise intensity increases or heart rate increases is because some individuals can't achieve as high an end diastolic volume, meaning that their heart chamber doesn't fill up with as much blood. And that's going to impact their ejection fraction. And remember, that's the amount of blood that is pumped out of the chamber. So they can't pump as much blood at a higher heart rate as they could at a lower heart rate. So in these individuals, even though their Q, their cardiac output, is still increasing, that cardiac output is increasing because of their heart rate increasing, not because their stroke volume is increasing. So again, figure 12.9, it just illustrates that there's differences in how individuals respond to different cardio exercise programs with respect to their stroke volume. Now let's look at VO2 max. And VO2 max is the highest oxygen use an individual can attain during physical exercise at sea level. It's how we quantify aerobic fitness. And factors that can determine our VO2 max is the ability of the heart to pump blood, and remember that's our cardiac output. The oxygen carrying capacity of the blood, and that's determined by its hemoglobin content. The ability of the working muscles to accept a large blood supply, and that's going to be determined by the capillarization within a muscle. And then the ability of the muscle cells or fibers to extract that oxygen from the blood and use it to produce energy. And that's going to be dictated by the number of mitochondria as well as aerobic enzymes present. In figure 12.10, we've got oxygen uptake versus work rate. And a common test to measure work rate will have the subject run on a treadmill and will periodically increase the speed or incline of the treadmill until the subject reaches exhaustion. So as you can imagine, not a super fun test to do. During the work period, we're going to measure both the inspired and expired gas and analyze that. And so figure 12.10 shows a graph of VO2 max versus work rate. We can see the red line, and it increases exponentially until a maximum is reached, and that's the VO2 max. Now, what would you expect to see in a less trained individual? As you might guess, it's going to level off sooner. So they might not get to 6, 7, or 800 watts. They might level off at 300 watts, or they might only be able to get to 8 miles or 6 meters per second, 8 miles per hour, 6 meters per second on the treadmill. So for VO2 max, we want to bring them to their maximal effort so we can associate their work rate with their VO2 max. We could also put a heart rate monitor on them and get their max heart rates at VO2 max as well. So this testing, it's not for sedentary individuals. We're not going to take a couch potato off the couch and throw them on this treadmill test. It's only for a population that's healthy enough to experience a maximal test. So Seeing figure 12.10 again, what's the difference between our two scores, our red line and our blue line? Who has the higher VO2 max? Well, I'm hoping you recognize that the red line has the higher VO2 max because they level off or reach their VO2 max at a higher work rate compared to our blue dotted line. So that's it for video 3, chapter 12, and we'll finish off chapter 12 with video 4 next.